Okay, ladies and gentlemen, good afternoon. Let's continue with Chapter 6 in the textbook of Cengel and Ghajar. Chapter 6 is on the fundamentals of convection. And the paragraphs we are going to do is paragraph 6.1, which is the physical mechanism of convection. And then paragraph 6.2, I'm going to go over it very, very quickly because you already did that in fluid mechanics. That's the classifications of fluid flows, and their issues are addressed like viscous versus inviscid regions of flow, internal versus external flow, compressible versus incompressible, etc. And then also the velocity boundary layer, which you also did last year in MTV 310. And then for the first time, we are going to introduce the thermal boundary layer, which have many similarities with that of the velocity boundary layer. And then paragraph 6.5, laminar and turbulent flows, 6.6, heat and momentum transfer in turbulent flow, and 6.7 is the derivation of the differential equations, 6.8, the solution of convective equation for a flat plate, 6.9, non-dimensional convection equations and similarity, 6.10, functional forms of friction and convection, and 6.11, analogies between momentum and heat transfer. So it's quite a long paragraph, but we are not going to spend 2 or 3 weeks on it because a lot of it you've already done in fluid mechanics. And then after chapter 6, we are really going to start with the heat transfer course, because up to then you've done all the basics. And chapter 7 will be specifically on external forced convection, chapter 8 on internal forced convection, chapter 9 on natural convection, chapter 10 on boiling and condensation, and then the most practical chapter will be the one on heat exchangers, chapter 11, and then, as you know, chapters 12 and 13 on the radiation heat transfer, that Dr. Leroux is going to do with you. So let's look at the fundamentals of convection, and specific the 3 different mechanisms of heat transfer. There are 3, and I've done it with the first revision lecture for you, where we have looked at conduction is the one mechanism. The other one is convection. And then thirdly, radiation heat transfer. Now, what those two have in common is that there must be an internal medium. There must be an internal medium. And the difference between conduction and convection is with convection, there is always a bulk fluid involved. And with conduction, there's an absence of the bulk fluid. That's the difference, and I'm going to make a sketch which is going to show you more clearly what's the differences between convection and conduction. The first one is where we're going to look at a flat plate, and this plate is being heated to 50 degrees Celsius, and then we have a fan there with air that is being moved with a temperature of 20 degrees Celsius and a velocity of 5 meters per second. Okay. And that would be the heat transfer rate, Q1. And this we are going to call forced convection. So the fluid is being forced over an object. It can also be fluid which is being pumped through a tube, for example. That is also forced convection heat transfer. The second type of convection is natural convection. And with natural convection, again, if this plate or material is being heated to a temperature of 50, and we have air at a temperature of 20, then these particles next to the wall is going to be heated, their density is going to decrease, and the buoyancy force is going to cause small currents flowing upwards, very, very small velocities. And this we call natural convection. And the third one is the very special case where we have air at 20 degrees Celsius. However, G is equal to 0. Now, if there's no gravity, if you think of these molecules, then there's no buoyancy force. So all these air particles is going to be around, and some of them are going to touch the surface, and then they're going to collide with the other molecules. So in this case, we will have conduction heat transfer. So forced convection heat transfer, natural convection heat transfer, and then thirdly, conduction heat transfer. So this would be Q3, and that one we can call Q2. The three different modes of heat transfer. Now, in general, the higher the fluid velocity will be, would cause that the heat transfer coefficient increases, or the heat transfer rate is going to increase in general. So if we think of this velocity, the higher that velocity will be, the more heat can be transferred. With natural velocity, with natural convection, you do not have any control about it, except if you can change gravity. Okay. If you increase the gravity force to 20 or 30 or something like that, maybe on other planets and places like that, then the natural convection will increase. However, if we take the gravity away, then there's no buoyancy force, and the heat transfer will be by conduction only. Now, convection heat transfer is actually very complicated in the sense that the heat transfer rate of heat transfer, or Q dot, is a function of quite a number of things. The heat transfer rate will be a function of viscosity, K, density, and Cp. Then it will be a function of velocity, surface temperature, the temperature of the environment, the specific geometry that has been considered, the roughness of the surface, as well as if the flow is in the laminar flow regime, the transitional flow regime, or the turbulent flow regime. But even although it is so complex, at this stage, how we solve convection heat transfer problems is to say that the convection heat transfer, heat flux, is the heat transfer rate divided by the surface area, and that is equal to a heat transfer coefficient multiplied by Ts minus T infinite. And that would be equation 1. Now, heat flux is the heat transfer rate divided by the surface area. I see you guys don't understand something. Is there a question? Okay. So this is what we call the heat flux, and this is the heat transfer rate. So with heat flux, our units is watts per square meter. Of course, you can also write the equation like this. The heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature difference. And then the units of the heat transfer rate would be watts. So at this stage, nobody has been clever enough to actually determine how this heat transfer coefficient can be solved by making use of the fluid properties, all these variables with a geometry which can be measured in some cases with L and in other cases with a surface area, and in other cases maybe the diameter, and also the roughness, how that can be taken into consideration, as well as the flow regime. Is the flow laminar, transition, and turbulent? We would actually like to take this heat transfer coefficient out and have the correct function. But so far, we have been unsuccessful in solving it analytically, and or even with all the experiments we are doing, we have challenges of getting the heat transfer coefficient. And this function will be very specific to certain geometries as well as to certain flow areas, like flow regimes like laminar flow regime, transitional or turbulent flow regime. Now, the thing with convection, and this you've done in fluid mechanics, is that with convection, there's always interaction between a solid wall and a bulk fluid. And one of the simplest cases of studying this interaction is by looking at the free stream velocity and then how it is going to change on a flat plate. That is the simplest of all the geometries. And you've done it last year, so there will be a no-slip velocity, which means that the velocity would be equal to 0, and that is the free stream velocity, V infinite, and this velocity 0.99 times V infinite. This is the boundary layer thickness. 99% of the free stream velocity. So if the free stream velocity is 100 meters per second, and we can measure the velocity as we go up here, we are going to look for the velocity of 99 meters per second. And that is considered as the boundary layer thickness. Now with heat transfer on a surface, we are going to have something similar but not the same. So if we look at the temperature as a function of x on a surface, then we're going to have a thermal gradient. But temperature is not a vector. So by using these lengths like this, we can show the value of the temperature. So the temperature is a function of y, of how we go away further and further from the wall. Now the important thing is that if this is the wall, then the heat transfer on the surface will always be from conduction to convection. So that would be the heat transfer rate of conduction, and that would be the heat transfer rate of convection. On the surface. It therefore means that we can say that the convection heat transfer rate, the flux, is equal to that of the conduction on the surface. And the conduction heat transfer is equal to minus K dt dy, where y is equal to 0. And what we can do is, let's call this equation 2 and equate equation 1 to that of equation 2. And the result will be that we can say that in terms of the heat flux is equal to a heat transfer coefficient multiplied by temperature difference is equal to minus K dt dy, where y is equal to 0. And from this, we can solve the heat transfer coefficient as equal to minus K dt dy, where y is equal to 0, divided by the temperature of the surface minus the temperature of the environment. So that is fundamentally the heat transfer coefficient. There's just one big practical problem, and that is normally we never have this temperature profile. It's very difficult to measure it and not really practical to use. However, that is really the heat transfer coefficient. So if we now look at the surface, and on the surface we've got T infinite at a certain velocity, with points 1 and 2, 3 and 4 and 5. And we would look at the heat transfer coefficient as a function of x. And then later on you're going to see that typically for points 1, 2, 3, 4, and 5, the heat transfer coefficients are actually doing something like that. There's point 1, point 2, point 3, point 4, and 5. Therefore, the heat transfer coefficients H1, H2, H3, H4, etc., is a function of position from the leading edge. At the leading edge, the heat transfer coefficient will be at its highest, and then it will decrease as we go downstream. So the heat transfer coefficient is not a constant over a surface. However, Okay, so we should actually write here heat transfer coefficient at 1 is not equal to the heat transfer coefficient at 2 is not equal to the heat transfer coefficient of 3. But what we do is, if we do those experiments and go and determine all these heat transfer coefficients, then for a specific body and for very specific conditions, we would, of course, go and determine the average heat transfer coefficient. So most of the heat transfer coefficients that you get in textbooks or tables, etc., is actually the average value, which is just convenient for design purposes. Okay. Next, we introduce the Nusselt number. The Nusselt number, NU, is equal to the heat transfer coefficient multiplied by a characteristic length divided by K. Take note, this characteristic length is not equal to the volume divided by the surface area as defined in the lump system approach. It is a characteristic length. And that characteristic length is normally the choice that was made by the person who's doing the experiments. So typically for a tube, internal flow through a tube, the characteristic length will be the diameter of the tube. If it is an aeroplane wing, like that, then the characteristic length would be equal to what we call the chord, the distance from the leading edge to the trailing edge of the wing. So the characteristic length is always given normally when the heat transfer coefficients are given. So again, it is in the fine print where you need to get the necessary information. Let's look at a flat plate where the heat transfer coefficient is equal to 100 watts per square meter degrees Celsius. LC is 8. The characteristic length, and we have air, and here we've got a plate with a thermal conductivity of, let's suppose it's copper, of 400 watts per square meter degree Celsius. Then we can calculate the Nusselt number as equal to LHC divided by K. In some textbooks, people will also make it clearer, and they would put in a footnote here that says Nusselt LC, so that you always know the Nusselt number is based on whatever dimension. So the heat transfer coefficient is 100, multiplied by the characteristic length, that is 8, divided by the thermal conductivity of the plate, and that is equal to 2. You all happy with that? You all shouldn't be happy with it because it's wrong. Okay. And I did it on purpose. So this is incorrect. because this should be the K of the fluid, the Nusselt number of convection heat transfer. Okay, now I didn't put in the K value of air, but maybe for some of you, if I've given the air value, would have used that value. However, I know from experience, many of you will use the K value of the solid, which means that the Nusselt number is actually equal to, again, LC divided by K. H is, heat transfer coefficient is 100, characteristic length is 8, and the thermal conductivity of air is equal to 0.03. So the Nusselt number is not equal to 2, but it is actually equal to 27,000. So this is correct. And this K value here is the K value of the fluid. And if you want to, in your textbook, maybe you can actually put a footnote in it so that you always remember it's the K value of the fluid, not the material.
K of the copper.
Yep. Oh, sorry. Yeah, watts per meter degree Celsius. Yeah. You understand that? So I hope you're not going to fall into that trap in the tests and exams. Now this Nusselt number that we see here, the definition of it, let's look at the physical significance of it. And we are going to do that by considering two fluid layers at the temperatures of T1 and temperatures of T2. So those are not flat plates, it is surface, it is fluid layers, and they are apart from each other the distance L, so that delta T is equal to T2 minus T1. And it can also be T1 minus T2, whichever one is the highest, come first. Okay, now, if the flow is in motion, then the convection heat transfer is equal to the heat transfer coefficient multiplied by delta T. So if those fluid layers are moving, then the convection heat transfer is equal to the heat transfer coefficient multiplied by delta T. If the fluid is stationary, then the heat transfer will be by conduction. For example, when there's no gravity. And then the heat transfer rate would be equal to K multiplied by delta T divided by the distance between the two layers, L. So what is important is the ratios. The students here on the side, maybe you will have to move in, please. So the ratios in terms of the convection heat transfer divided by the conduction heat transfer, the convection is equal to heat transfer multiplied by delta T, that term, and the conduction is K, delta T divided by L. And just to make it clear, that would be the K of the fluid. We're looking at the heat transfer in the fluid. This is not a solid we've got here at the temperature of T1 and T2. It is two layers of fluid. So you can also write this in terms of Kf. And if you look at this, what you will see is that this ratio is equal to the heat transfer coefficient multiplied by L divided by K. And it's the K of the fluid, and this is exactly the definition of the Nusselt number. So the Nusselt number tells us the level of enhancement of heat transfer. Enhancement of heat transfer. Enhancement relative to conduction. So if the Nusselt number is equal to 1, then we have heat transfer by conduction only. If Nusselt number is equal to 1, then we've got heat transfer by conduction only. Can be explained as follows. Let's suppose you put off gravity, then the conduction heat transfer for the flux, let's choose 5 watts per square meter. 5 watts per square meter. That is the conduction if the gravity is off, there's no gravity. However, if you put on the gravity, and now you go and determine the convection, and the convection is 50 watts per square meter, then the Nusselt number is then equal to the ratio of the convection heat transfer divided by the conduction heat transfer. And that would be equal to 50 divided by 5. That would be a Nusselt number of 10. What does it mean? Physically, it means that if your Nusselt number is equal to 10, your enhancement in heat transfer is 10 times more than conduction. Okay? If the heat transfer is by conduction only, then there cannot be any enhancement. So the Nusselt number can be, or will always be, larger or equal to 1. But the Nusselt number can never be smaller than 1. If you do a calculation and you get a Nusselt number of less than 1, then you must know you've made a calculation error. So Nusselt numbers smaller than 1 can never occur. The Nusselt numbers are always equal or larger than 1. Equal to 1 means the heat transfer is by conduction only. Right, that is paragraph 6.1. Paragraph 6.2 is classification. The classifications or the characterization of fluid flow. Classification of fluid flow, and all that this you've done already last year. So this is about the difference between viscous flow versus inviscid flow, internal flow versus external flow, compressible versus incompressible, laminar versus turbulent, natural or unforced versus forced flow, and steady versus unsteady. as well as 1, 2, and 3-dimensional flow. You should be familiar with this. We are not going to do that in detail, but just to help you with a few things that I know many of you battle, I would like to show you the following example. This is an aircraft engine. Let's suppose it's the engine of an Airbus 380. Then its engine, you're going to do this next semester, consists mainly of 3 parts. Here's the compressor, the first part. Here's the combustion chamber. And here's the turbine. Now the compressor consists out of blades that will direct the flow into a certain direction, and then it is going to compress the air to a higher pressure. And then after that there are blades again, and you get 6-stage or 7-stage or 8-stage compressors, looking something like that. Now this air will be compressed to a higher pressure. Then you will add some fuel to the combustion chamber and a spark, and then you've got an increase in temperature and pressure because of the fuel that is being added. And this gas now is going to then expand through the turbine. And again, the turbine is going to consist out of different rows of blades, what we call stationary blades. They do not rotate around. And then after that, there are the turbine blades, and you've got all these rows from one to the other. Very simple representation of the turbine of an Airbus. Now, one of the easiest ways to explain a few things is to make a graph of the density of a fly or something going through this turbine. Okay. And this fly can actually measure the density and or pressures at different places. So before the turbine is equal to 1, and then here there's going to be position 2, there's going to be position 3, and there is position 4, etc. So if the fly is now going to measure the density as a function of distance as it goes through this turbine, then when it measures the density there, then that is going to be the density. If the fly can stay there all the time, it's going to measure a certain value of the density, and that density is not going to change. Sorry, this is not position, this should be time. Okay. So it will stay constant. At point 2, there will be an increase in density. So that is what's happening point 2. And the density is going to increase all the way. I'm running out of space here. Well, let me do it like this. I'm going to need 2 graphs. Okay, density as a function of x. So if the fly could stay there, it will measure a constant density. It is not going to change. However, if the fly follows the air stream, it's going to come to the inlet of the compressor, then it will be compressed. It will be compressed more, so that would be station 1, that would be station 2, 3, etc. Going through the combustion chamber, all the way, it's there. And then after that, it is going to expand, and it's going to do something like that. It's going to change. If you measure the density as you go through that turbine, that is typically how the density is going to change. However, if you measure the density only at one point, that density will stay as a constant, as a function of time. So that's time. Okay, and there would be 0.3 and 0.4 and 5. The density would increase as a function of time. Now this graph tells us a few important things. The one is, if we stay at this position, then all this flow is going to be steady. Why? Because it doesn't change as a function of time. Okay. So it is steady flow if we consider the density at any specific time. If we look at this, we are going to say this flow is compressible. Because we can see how it is being compressed. Now, although it is being compressed, we have to distinguish between when can we consider the flow field as compressible and when not. For that, we are going to look at the ratio of the velocity divided by the velocity of sound. And for air at 20 degrees Celsius, the velocity of sound would be about 350 meters per second. So we normally say that the Mach number, if it's larger than 0.3, I think, then the flow is being considered as compressible. So this flow is steady because it's not a function of time. And here, the flow is going to be compressible, but here it's going to be incompressible. And again, here also, it is going to be incompressible here. Okay, paragraph 6.3 is about the velocity boundary layer. The velocity boundary layer. I'm just going to introduce it because we are not going to have enough time to go through it in detail. And my sketch, I normally would like to use much more board space. So that is being illustrated on a flat plate where we've got a uniform inlet velocity. V infinite. And on this plate, we are going to have 3 different zones with different characteristics. There's going to be a laminar part, there's going to be a turbulent part, and there's going to be a transition part. And this distance is called the critical distance, XCR, and that is the distance from where the flow would start changing from laminar flow to transitional flow. Right, ladies and gentlemen, we are out of time. Remember, on Thursday you're writing your test. You will need your textbook, and some students already asked, so it is the rules are exactly the same as that of last year. You can make notes in your textbook, everything. However, you just cannot here in the back where there are a few open pages, or at other places go and spot a problem that you think we are going to ask. But furthermore, you've got all the information you want. Thanks very much, and then I'll see you again next week.